Okay, now that we got 9.2 out of the way, and 9.2 is a little bit more indirect, okay? 9.3 is a little bit more method, okay? And so 9.3, I think your teacher does this too. 9.1 is sort of almost a throwaway section, and I usually folded it in with 9.3 since it kind of they both deal with solutions to differential equations. So I'm going to start out with a couple of problems that are sort of indicative of 9.1, and then from there we'll move on to 9.3, which we've already sort of covered a little bit, and we've done a couple examples of. It has to do with separable differential equations, so finding both general and specific, solutions to differential equations that are given. So let's say we're given y prime minus 8x is equal to 0, and I want to confirm that y is equal to 4x squared is a solution to that particular differential equation, okay? Here's the thing. Very, very easy. All I need to do is take the derivative of this, and then I just need to take it and substitute it in. And so 8x minus 8x is equal to 0. 0 is equal to 0, check. Okay, I have confirmed that y is equal to 4x squared is a solution to that differential equation. They can, however, be a little more complicated, and let's say that I have y double prime minus 2xy prime plus 8y is equal to 0, and I need to confirm that y is equal to 4x to the fourth minus 12x squared plus 3 is a solution. Well, the first thing I need to do is I just need to differentiate this twice. That's 16x cubed minus 24x, and y double prime is 48x squared minus 24. Then I simply need to take this, plug it in for y double prime, take this, plug it into y prime, and see whether I get a true statement. If I get a true statement, it is indeed a solution to that differential equation. If I get a false statement, then it's not true, and it isn't a solution. Okay? The only thing you really need to watch out for, let's see, 4x to the fourth minus 12x squared plus 3 is equal to 0 is just distributing that negative. So we get 48x squared minus 24. That's going to be minus 32x to the fourth plus 48x squared plus 32x to the fourth minus, and of course 8 times 12 is, that's right, 96x squared plus 24. Whew. Okay, now just if they all cancel out, we're good, okay? Negative 24 cancels out with positive 24. That's easy enough. Negative 32x to the fourth cancels out with positive 32x to the fourth. And this one plus this one is positive 96x squared, which of course cancels out with negative 96x squared. 0 is equal to... Now, like I said, this is a pretty straightforward kind of idea. Let's go ahead and do a really obnoxious one just for the sake of argument. And then we'll move on to separating variables and solving differential equations. Let's go ahead and confirm that one. At which point we go, ew, it's so icky. And the reason it's icky, for lack of a better word, is the fact that you have to use the product rule, okay? So let's go ahead and do y prime. Y prime is e to the x times 2 cosine 2x plus e to the x times sine 2x. And then, of course, you have to do the product rule twice, okay? So you have e to the x, and we'll take the derivative of the first times the second plus the first times the derivative of the second. Now, the derivative of the second is going to be negative sine, right? It's going to be negative 4 sine 2x because the chain rule 2 combines with the 2 that's already there, plus Now, obviously, this is identical to the original, and therefore I can just sort of copy this if I want to. E to the x, 2 cosine 2x, okay, plus e to the x sine 2x. Okay, well that's kind of obnoxious, but, you know, we can sort of combine things and make it a little bit easier on ourselves. That's going to be 4 e to the x cosine 2x when I combine this term and this term. And then the next one is going to be, well, this one is going to be -4. That one's going to be +1. So -3 e to the x sine 2x. And that's y double prime simplified. Okay? So y double prime is 4 e to the x cosine 2x minus 3 e to the x sine 2x minus 2 times y prime, which is, of course, e to the x. Actually, let's go ahead and put the 2 right there. Cosine 2x plus e to the x sine 2x minus our plus 5 e to the x sine 2x is equal to 0. Whew. Okay, let's go ahead and distribute, and let's see if everything cancels out, which it should, unless I've made an arithmetic error somewhere, which is always a possibility, but let's hope I didn't, because then it'll take me a second to find it. Nope, it looks like I've done a pretty good job. And there you go. Now, 4 e to the x cosine 2x, -4 e to the x cosine 2x. Negatives of each other cancel out. +5 e to the x sine 2x, and then -2 and -3 make a -5 e to the x sine to the 2x. Boom, 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 and I get 0 is equal to 0, and cha-ching! I have confirmed that that is a solution, that this equation is a solution to that differential equation. I'm so proud of me. All right. Well, that sort of gets out of the way a little bit of the 9-1 stuff in terms of, you know, generally what's going on with differential equations, which we've picked up a whole lot, you know, just by means of going through slope fields and for those of you who are BC kids, a little bit of Euler's method and stuff like that. Let's go ahead and take a look at y prime plus 4xy squared is equal to 0. And let's say I want to find what's called the general solution. Now, I'm looking for a general solution, not a particular solution, because I'm given no initial value. If I'm given no initial condition, I cannot find a particular solution, and I need to remember that a differential equation describes a family of curves and not one particular curve. It only describes one particular curve when I'm given an ordered pair, okay? So we have this. We need to remember that y prime is dy dx, okay? So dy dx, and then let's go ahead and shove that over to the other side. Can I get all of the y's together? Sure, okay, I can divide both sides by y squared. Can I get all of the x's together? Sure, I can multiply both sides by dx. So what I'm going to do is I'm going to divide both sides by y squared, and in the same step multiply both sides by dx. I have separated and isolated the variables. The y's are with the dy's, the x's are with the dx's, and now, of course, I can go ahead and integrate if I want. And, you know, for those of you who are, looking to undo the power rule, that might be a better form to put it in. We're going to integrate both sides. That becomes y to the -1 over -1, or -1 over y. And this becomes -4 1/2 x squared, and then plus c. Well, here's the thing. I can go ahead and keep switching the c value. C really doesn't matter to me. But, you know, I don't like the fact that I have negatives here. So let's go ahead and multiply through by a negative. I have 1 over y is equal to 2x squared plus c, or y is equal to 1 over 2x squared plus c. That should be my general solution. Okay? And if you don't believe me, I mean, you can obviously go ahead and differentiate. And go ahead and see if differentiating gets you back to the original equation, or if once you differentiate you can work back to the original by changing the form and stuff like that. But let's go ahead and push on. I sort of left enough room to do another problem up here in this other column, so let's go ahead and work up here. I have 1 minus x squared y prime is equal to x y. Right? Now, I see this over here, and I know that this is going to be dy dx. I'm going to go ahead and do it in 2 steps instead of 1. Let's go ahead and turn the y prime into dy dx and divide both sides by that radical. At this point, I can divide both sides by y and multiply both sides by dx, and so I'm going to get dy over y is equal to x root 1 minus x squared dx. Now this over here winds up being u sub, okay? The u sub actually winds up being relatively easy. So once we decide we want to integrate, this winds up being obviously a natural log function, but we'll go ahead and sort of hold off on that right now. Minus x squared dx, that becomes -2 and -1/2. Okay, so this becomes -1/2 u to the -1/2 du, okay, which then becomes 2 u to the 1/2, and that makes -1 minus x squared plus c, and that's natural log of y. Okay. It depends on what your teacher wants, and obviously I've said this before, what form you leave it in has everything to do with what you're going to wind up doing with it. This is an implicit equation, and as such it's a legal form to leave an equation in. Now if you're being asked for a function, you're gonna have to fiddle with it a little bit. If you're asked to isolate y, you're gonna have to fiddle a little bit with it. You're gonna have to ask your teacher exactly what to do. But obviously, from here we exponentialize, and then we use a little bit of. We wind up using a times e to the -1 minus x squared. Because remember, this winds up being e to the -1 minus x squared times e to the c using rules of exponents. And that e to the c is basically what I termed a. Okay? And so what we have here by separation of variables is just a very straightforward exponential, sort of in the family of exponential curves. I mean, obviously the exponent right there is a little bit of a strange x expression. We're not used to seeing that. It's kind of hard to visualize what that actually looks like in our heads, but whatever. Let's go ahead and actually I think right about now is probably a good place to stop. We'll go ahead and pick up in the next one. We'll do a couple more examples of finding the general solution before we actually get to some initial value problems, and that'll take us to the end of 2. And at that point, I'll make a decision as to whether we want to do 2 or 3 for this particular section. As per usual, email me with any questions that you might have, and I will look forward to hearing from you.